example 1 is also a great application of where this idea that we're doing can be used in real life. It's another volume question, and what we're starting with is a piece of cardboard that measures 30 centimeters long and 25 centimeters wide. And you're going to cut squares out of each of the corners. So you cut a square out here, cut a square out here, cut a square out here, and cut a square out here. And then if you fold along these green lines, can you see that that would make an open-ended box? And the interesting thing is that the bigger, I'm going to put this as X on all of these corners, because these squares are all the same size. The bigger the X you cut, the more material or more cardboard you're throwing away, right? Because when you cut that out, that gets thrown away, and then it gets folded up. But the smaller that X is, the smaller your height is, and if your height's too small, you won't have any volume. So it's kind of counterintuitive. I need height to get a better volume, but the more height that I get, the more cardboard I'm wasting. So now the question becomes, what is going to be the volume that's the maximum? How much should I cut out to create the biggest one possible? Well, first of all, we're going to write an equation for the volume. And it's not just X here, 30 here, 25 here, because now that you cut out X, can you see that this green line here on this side will be 30, but 2 X's have been cut off both sides. Same thing here, this one will be 25, but 2 X's are cut off. So this side is 25 minus 2X, and this side is 30 minus 2X. And our volume, length times width times height, there's an expression for our volume. Just like in our intro example, we can graph this. So part B, after the graph, what do we need to do for our graph? First of all, we have to think about our end behavior. And again, this is going to be, has a minus 2x, this has a minus 2x, and this has an x. If you multiply those all out, just the x parts, you would get a positive 4x cubed plus dot, 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 which is an odd function. Odd functions, end behavior acts like a line. Here's our line with a positive slope. There's our end behavior. Y-intercept, super easy, plug in 0 for x. The last one is just a 0, so it's going to be 0, 0. And x-intercepts are also easy because it's already factored, right? Plug in 0 for y. So again, it's important that we're able to graph this by hand, even though we're going to be able to use technology. Graphing it by hand is going to tell us we've got at 0, at 12.5, and at 15. And behavior says down here and up here. Each of those has a multiplicity of 1. The graph is going to go straight through. We draw our curve straight through, matching up with each of those points. Again, it's a real-life example. This is our volume. This is our x. right? The y-axis, our equation isn't y equals, now it's volume equals, so your y-axis becomes your volume. Your variable is x. If we think about x in this situation, x is the height, so you might even want to write out in words here, there's your volume, x is your height. What's the only part that makes sense? Is this section right here. Why? Well, you can't have negative volumes, so these parts should not make sense. Here I have a positive volume again, but if you think about cutting out an x that is bigger than 12.5, look at your original picture. As soon as you cut out something bigger than 12.5, there's nothing left. Your cardboard's all gone. You're like, oh, this isn't a very good box. And so even though the graph shows a positive value, yeah, cut out 20 and you get a positive volume. Well, in real life, if I cut out 20, there's nothing left on this side, nothing left on this side. How is that even possible to get a volume? So this is the only section that makes sense. And now we want to go to Desmos and graph this. And I'm going to close Desmos down and start it again, just to see if we can practice working with how to work with the window to make it match up. So we had 25 minus 2x, 30 minus 2x, and x. And again, look at the window that we started with. We know from our graph that we want to see between 0 and 12.5. So there's my 12.5. But if I zoom out this way, with just using my scroll button, it's zooming out of both my x's and my y's, where in reality, I want to see higher with my y values. So I'm going to use the tool button, but before I use the tool button, I'm going to go back to my question and just do an example. Let's do an actual example of what you think would be reasonable to cut out. What kind of height do you think might be a good example? 2? 4? I think 10, once you get to 10, then these other sides get too small. Should we try 5? Let's say we try 5. If this is 5, then you're going to take 10 off of this side will be 15. You're going to take 10 off of that side, that's 20. 20 times 5 times 15 would give me 1,500. So I'm going to use that actual example to help me with my window. I'm going to go to my window, and I know that my y-axis needs to go up to at least 1,500. So I'm going to change my maximum y to 2,000. Oh, nice. Look at that. And we see our graph more like we drew. Now I can click on the graph, click on the maximum. I was close with 5. 4.52 and 1512 is the best answer. So we'll go back here. We can go to our graph. 4.52 and 1512. What does it say in part C? It says, to the nearest cubic centimeter, what is the maximum volume? So the max volume, well, volume is your y coordinate. (1512) centimeters cubed. I'm just going to go back to decimals to check if my rounding is fine on that. 1512.04, yes. And second question it was asking, what size of square to the nearest cubic centimeter, what size of square does it say to the nearest 10? So the square size of the square is your x value is to the nearest tenth, 4.5, and then if we take that 4.52 and subtract it off of the 30, 4.5 times 2 would be 9 point, it'll end up being 9.04, so we can subtract 9 off of the 30 side will be 21. 9 off the 25 centimeter side would be 16. Oh, 25.0 to the nearest 10. Yes, technically I should double check that. 4.52. Get my actual 3 decimal, 4.527. 4.527. I had a rounding error. When I used all the decimal places, it was 20.9 instead of 21. It was 15.9 instead of 16, and 4.5 was fine. So again, we try not to round until the very end. Again, you could do this on your graphing calculator as well to get that maximum dimension. Questions for practice on this one? Are 3, 4, 5, 6, 9, and 10.